the order of chapters that I've presented for this semester. Maybe I should have mentioned this chapter earlier before the mistake, but however, as usual, chapter 5 and 6 will be assessed during the final examinations, and the chapter on mixture is related to the group assignment. Okay, so for those who already successfully attended the test 2, I would like to state our thank you. And I noticed that some of you still having difficulties to submit using the platform, which is through the Otter platform. So you need to really work out your strategies and planning when we're going to have our final examinations, which will be in July. Okay, because as per regulation, ikut peraturan universiti, as per regulation of the university, submission for final examinations is only valid if it is submitted through the Otters platform. So I know that the situation is challenging to some of you, but as best as possible, please try to work out how you're going to complete all the assessment, especially for the final examination, using the Otters platform, because that will be the recognized submissions by the universities. Because through Otter, we can record how many students actually completed the final examinations, and then that will be the guidance as to how we can determine the numbers of attendees and relate with the answer script that the student will submit. Okay, so again, last time some of you tried to use the WhatsApp, so I just would like to remind you, we can only accept the Otter platform for the final examinations. Okay, so as best as possible, please work out ways and planning for the incoming exams, which is due in July. Alright, so inshallah today we'll be entering our last chapter, which is on the internal combustion engines. I think in the RPP, internal combustion engine is in chapter 5. Maybe I'm mixed up in terms of the order, but the assessment for chapter 5 and 6 will be through the final examinations. Okay, so internal combustion engine, so simply we call it as ICE. Basically a thermal system, or we could say same with the heat engine process. The notes that I used for this chapter is taken from Dr. Nur Ashikin, PM Dr. Nur Ashikin, and then if you guys actually access the Google Classroom, okay, if you just presenting now, just to show you where is it? Right, okay, I'm going to present the entire screen. On the Google Classroom, here you can see this, the attendance for today, and then also there is also the padded link to the internal combustion notes. So if you click on the link, you will arrive on this page. So there are a few slides. So this one is the brief slides on the internal combustion engines, and then there's another slide from Associate Professor Dr. Ashikin, which is I'm using today. And there are also additional notes and slides, which simply an extended content for the 2 slides uploaded here. Okay. Please refer also to this additional note from the textbook, not from Cheng and both, but from different authors, because it gives out a good example. And then if you have the soft copy for the whole textbook, it will be much better. Okay, so please after the class and also for the remaining of the semester, refer to this book. Okay, already reduce the chapter on internal combustion engines as is one particular note. Okay, so you can refer mainly from the slide from PM Dr. Rashikin, and then the additional from the book by I think Shapiro, and I remember the author, but I've already selected the chapters which is related to internal combustion engines. Okay, ready for that. Right, coming back to the slides. Right. So we talk about internal combustion engine because it's the one of the important devices in the engineering world, and it use a lot of the thermodynamics fundamentals, and this is also related to the heat engine concept. Okay, because we converting the heat from the chemical energy sources into mechanical work. So if you have the heat engine schematic, you have the concept of the high temperature reservoir. Okay, high temperature reservoir, and then you have the heat engine, and then you have the heat sink or the low temperature reservoir. So for the internal combustion engine, the high temperature reservoir comes from the chemical energy reactions. Okay, when you burn the gasoline air mixtures, you burn the diesel. So the source of the chemical energy is when you have the mixtures between fuel and air. Okay, and fuel, as you purchase your common fuel from the petrol station, is what we consider as the layman term as the petrol. Okay, and also as the diesel and so on. And then the petrol has two different grading formulations, where we have the 95 or G7. Diesel also have a different grading, so we have the diesel conventional, or we have the B5, which means that it's blended to biofuel, and then we're going to have the in the future B20, okay, which means a 20% blended with biofuel, as well as what we call it the Euro diesel, Euro 5 diesel. Okay, so these are the fuel. The resulting combustion process will produce the necessary energy that the heat engine will convert into a mechanical output. So this mechanical output is the one that's going to drive the gearbox, will drive the transmissions, the driving axle, and at the end will drive the wheels, so that the car will obtain the forward motions. Okay, so the source of energy is the chemical energy. Okay, so the applications are a lot, as you know, as a land-based transport, as a marine-based vehicle, also for the airborne purpose. And in the starting from mid 2020, no, sorry, not from early 2000s, so 2005 and above, the shifting from ICE to fully non-fossil fuel has been happening. So in the engineering sector is try to reduce the dependency on fossil fuel base. Okay, the gasoline, diesel, everything is basically fossil fuel based, and as you know, I think most of you have this awareness, we are moving towards electric vehicle, but the challenge are still abound because for example, in Malaysia, we have this challenge of infrastructures and the challenge of having to have a good supply for the battery manufacturers, and also the process that we have once the vehicle is not in use and so on. Okay, and there's also the usage of internal combustion engines for the portable generators or prime mover inverse cutting machine and so on. And I have one student, PSM student, right now is working on what she's doing is she is investigating the diesel generator, okay, that are being used by a power plant in Sabah, okay, diesel generators to provide electricity. Okay, even though the transport sector will be jumping from fossil fuel based to electric powered propulsion system, but in the power supply industry, some of the generators are still using the diesel fuel, and diesel fuel engines, or we call it the heat engines, they can last long. So even though you don't have the implication of a petroleum base on the road and so on, but there are still sectors that still relying on the use of internal combustion engine. So that's why in terms of the syllabus, we still need to have a brief understanding on the internal combustion system, the air cycle, auto cycle, diesel cycle, and so on. Okay, so when we talking about internal combustion engines, so we need to refer also to the two main factors when you're talking about ICE: the geometric factors, factor geometries, and also the thermodynamics factors. Okay, the geometry is what we talking about, the physical parameters of the engines. Okay, so we have the cylinders construction. So we have the piston, which is moving outwards and downwards as a result of the explosion. So you have the explosion here from the chemical reaction. So it will give out a big explosion. So it pushed down the piston downwards. Okay, and then once the combustion is completed, then you get rid of it through the exhaust valve. Okay, so this is a simple single cylinder setup. So you have a cylinder, you have a piston. So you mix everything here, create the explosion. The explosion will create the downward force, and then you then convert the rotary motions to become a linear motions. So this is the connections to the gearbox, powertrain, and so on. Okay, and similar with the reciprocating compressor, there is also a geometric presence of the clearance volume. Okay. In chapter 3, you already learned about the reciprocating compressor. You're going to have the same piston moving outwards and downwards, but the difference that for the ICE, okay, in the ICE you have this thermodynamics effect from the combustion. So you have the explosion in the internal combustion engines, but you still going to have the volumetrics analysis, which is based on the clearance volume. You still have the sword volume, you still have the piston, okay, the piston diameter. You're going to still have the diameter, and then what be the stroke, where the sweat volume, and so on. Which means that you're still going to apply the volumetric efficiencies, okay, concerning to the engine and so on. Okay, there's also top dead center, bottom dead center, similar as the reciprocating compressors concept. In addition, for this chapter, the only difference that you have the explosions ongoing. Either you use the petrol fuel or you use the diesel fuel. Okay, sorry, somebody is coming. All right. Okay, so how we can classify the engines? Why we need to classify? Because each type of internal combustion engine will produce different outputs. You use it for different purpose, and then you will need to consume different type of fuels. So in general, we can classify into two general categories, which is depending on how the combustion process is initiated. So the first category is what we call the spark ignition engines, and then the second category is the compression ignitions. So the distribution of a spark ignition engines that it use liquid fuel such as gasoline or petrol. So in our scenario in Malaysia, is either you are using RON 95 or the RON 97. So this is what we call as petrol or gasoline. I think in the US they call it as gasoline. Okay. In the Europe they call it petrol. In the ASEAN region we call it petrol. In Malaysia we call it petrol. And if you are traveling to Thailand, for example, you're going to have a mixture of petrol with ethanol. Okay, but still they are using the spark ignition engines. Okay. Another way to describe the spark ignition engine is that I stand for the emissions. Okay, the emissions for the combustion is initiated by the presence of the spark. Okay. Spark coming from the spark plug. I think most of you have access to a motorcycle. Okay, so you can actually search using the Google after this, or using the relevant literature engines, how the spark plug is functioning. So you have to initiate the ignitions, and for the spark ignition engines, we call it spark ignition because the ignition process is created by way of the spark that is generated by the spark plug. Okay, so you have the mixtures inside the chamber. So you have the fuel air mixture, so they have fuel, you mix with the air, and then this mixture you throw it into the cylinder, or we call it the chamber. So, and then compress the mixtures, and then once it reach the required position, okay, I think there should be a sketch here. Okay, if there's no sketch, then no problem. I will show you tomorrow, inshallah. So once you compress the air fuel mixtures, the spark plug then start to create the spark, and as a result, you produce explosion. Okay, and then the high pressure of the gases pushes the piston downward, producing a power stroke. And then the crankshaft, which is moving downwards, because of we're dealing with the crankshaft, which is has transform the downward motion into a rotary motions, and then it carry to the powertrain and so on. So you have at the end the vehicle moving forward. So when you say spark ignitions, again a reminder to you, we are using petrol or diesel fuel, and in the modern understanding, the petrol in some countries are mixed with biofuel. Like for example, in Thailand, the biofuel being used is ethanol. Okay, so that's the first classification for the internal combustion engines. Okay, the next one is what we call it the CI engine. C stands for the compressions. In Malay, we call it engine jalaan mampatan. For the spark ignitions, we call it jalaan pencucuhan, or the spark ignition. For the compression ignitions, the ignitions of the engine is due to the compressions. In contrast with the spark ignition engines, only air is entering the cylinder. Okay, just now the spark ignition is talking about mixtures of fuel and air, but for the compression ignition, only air is being pushed down into the cylinder. Okay, yang masuk ni cuma udara sahaja. For the spark ignition, you have the mixtures of fuel and air, but for the compression ignitions, what you compress, what you put into the chamber is only the air. And then the piston will move outwards and will compress the air. And once it reaches the required pressure and temperature, there is an injector on top of the cylinder where it will then inject the diesel fuel. So by way of Adair's equation of states, so when you have high pressure and high temperature, okay, the moment you inject the diesel fuel, it will create combustions, and then the combustion will prolong and start off the mechanical motion of the piston moving downwards, and then convert into rotary motions, and then rotary to the powertrain and so on. Okay, so those are the two description for the spark ignition and compression ignitions. Okay, and then the type of fuel that we inject into the compression ignition engines is, in the layman term, we call it a diesel fuel. Okay, and also what we call as the biodiesel blended fuel. Okay, so if you go to the nearest petrol station, we call it a fuel station or petrol station, or the layman term is petrol station. So we have the B5, which means the 5% blended from the biodiesel fuel. Okay, or you call it Euro 5 diesel. Okay. Based on the description that I've mentioned just now, it also shows why you cannot use diesel fuel into a spark ignition engine, because the way the fuel is combusted is different. If you have the time, if you, for example, pour tuang sejumlah petrol dalam satu bekas inside a known size of a container, and then you pour the diesel into another similar size of container, and then you leave it outside for like not half, I think about little, for a few minutes, and then you will notice that the petrol fuel will easily vaporize into the air, and then after a certain time you're still going to have the diesel, but the petrol is already vaporized into the surrounding. So this shows that for you to manipulate the chemical properties of the petrol fuel, you need to have the spark ignitions to initiate the combustions. And for the diesel fuel, for you to initiate the combustions, you need to encourage the high pressure and high temperature. So that's why if you are burning diesel fuel, you need to use the compression ignitions. If you are dealing with petrol fuel or a gasoline fuel, then you need to use the spark ignitions. Okay, if you mix up the type of fuel to the different type of engines, you may end up with having no combustions and nothing is happening or nothing is produced by the engine. So you need to really clean up the engine and then use the correct type of fuel for combustions. Okay. In both engines, the combustion gases are eventually exhausted out of the cylinder so that the fresh air mixture can be induced into the cylinder to continue the thermodynamic cycle. So by way of this physical or you call it a geometrical based operation, so we can then define, therefore, working on an open cycle is the characteristic of all ice, since the working fluid does not undergo a complete thermodynamic cycle. So this is the first assumption that we take for analyzing the internal combustion engines, where we then use the approach of a open cycle analysis. Okay, and then the definitions for the combustion ratio, the maximum volume divided by the minimum volumes, and then similar as the chapter 3, you cannot ignore the presence of the clearance volume. Okay. The compression ratio is volume ratio and it's not the pressure ratio, so it's totally based on the volume available. Okay, just want to highlight the concept of bore and stroke. Okay, you know that the cylinder is basically a cylindrical shape like this. Okay. And then the piston is basically of cylindrical shape as well. Bore is also equal as diameter. Another name for bore is diameter, and diameter is basically the distance of the face of the piston. Okay, in some question you're going to meet a statement saying a square engine. So what does a square engine means? A square engine, what does it mean? That it means the bore size is equal to the stroke size. So you call it as a square engine. Okay, so if the question asks you what will be the if the engine is a square engine, so what is the dimension of the engine stroke, given that the bore is 10 centimeter? So the answer is 10 centimeter, because the square engine is that the bore and stroke is of the same dimension and sizes. So it's very compact engine. Okay, and then bore is also diameter. So when you have the diameter, you know the stroke, then you can calculate the capacity or the volume of the engines. Okay. And then we have the mean effective pressure. It's just a conceptual, even though it's a conceptual or pressure, okay, we can calculate mean effective pressure, because we want to know for engines that have different sizes, what will be the useful energy that we can produce through the combustions, because the area of concern is the area inside the cycle. So you define as the mean effective pressure. Okay. Sometimes you'll be asked to calculate the mean effective pressure. because how we can compare the performance of two different engines is by calculating the mean effective pressure. You cannot simply say that the 2-liter engine is better than the 1.5-liter engine, because you really need to, or you can, or you want to simply say 2-liter petrol is much better than 2-liter diesel, because it's just a direct comparison which doesn't carry analysis on the thermodynamics effects and of the engine. So you need to analyze based on the geometrical and also the thermodynamic effects. So one of the parameters that you use is the analysis on the mean effective pressure. Okay. For the same engine size, MVP can be used as a criteria of parameter to compare the engine performance. So that's why we need to do the calculations. In theory, the engine with a larger value of MVP delivers more network per cycle and thus perform better. Okay. And then the calculation for the mean effective pressure. So work is force time distance, and then you know the pressure. You then can play around with this equation, and then you work out the mean effective pressure. And the displaced volume is the volume where the piston travels from the TDC, top dead center, into the BDC, the bottom dead center. So that's your stroke. If that is your stroke, then you know this is the volume that of concern. Okay, because it depends on the swept volume, the engine, and then you can work out the. If you know the work produced, then you can work out the mean effective pressure. The next classification of the engines, the first one is based on the SI or CI. Okay, the first classification is based on spark ignition or compression ignitions, and then you know that spark ignition will use petrol equivalent fuel, and the compression ignitions we will use diesel equivalent fuel. Okay, another way to define the internal combustion engine is by looking at how the engine is operating. Is it using a two-stroke cycle or four-stroke cycle? Most automotive engines is operating using the four-stroke cycle, which means that every fourth piston stroke is the power stroke. One movement downward is one stroke, second stroke, third, and fourth is a four-stroke. Okay, equal to the movement of the piston. So two-stroke, which means that the piston only moving downwards, upwards, and then it starts to produce the work. Whereas for the four-stroke, it requires movement downwards, upwards, downward, upwards. Okay, in total 4 movements for it to produce work. So just looking at here, you can see that of course two-stroke will produce much faster output from the combustion process. Okay. And once revolutions, because the piston going downwards and then outwards, so it's equal to 1 revolution. Satu pusingan crankshaft, okay, bersamaan dengan 2 kali stroke. So the two-stroke cycle is only requesting for 1 revolution to produce the work, which means for the 4-stroke cycle, it requires 2 revolutions to produce the work. So that's how we differentiate between the 4-stroke and 2-stroke cycle. You can observe the animation. Stroke number 1, the induction process. The inner valve is opening and then the exhaust valve is closed. The piston is moving from bottom dead center to top dead center, and air fuel mixtures is induced or being pulled inside the chamber. And then once it's enter, it compress, fire, exhaust. So that's the 4-stroke of the process. induction, compression, working or power stroke, and then the exhaust stroke. So if you look at the number of revolutions, it requires 2 revolutions per cycle. Okay. So this is how the 4-stroke engine is working. And during the induction stroke, inlet valve is open. During compression and power, both valves are closed. Tutup, tutup, power. Okay. Which one is intake? I think this one is intake. Okay, this one is intake valve. This one is exhaust valve. Okay. So during the exhaust stroke, the inlet valve is closed and the exhaust valve is open, so that you can push out the byproduct of the combustion, which is the exhaust gas, outside the cylinder. So piston moving downwards, compress, you initiate the combustion. So this is the ignition process. Since you are using spark plug, so that's why we call this a spark ignition engine, because you need to have the spark plug to create the spark to burn the air and fuel mixture. So the ignitions can occur before the compression process ends. And this is the PV plot for the process. So if the pressure of the system is higher than the atmospheric pressures, it's happening during the exhaust stroke, or you can have it during the intake stroke. For 4-stroke engine, you can arrange, if you have more than one cylinder, you can either have it as a V shape, or you have it as an inline. So here you have one cylinder, second, third, and fourth. Third, second, third, and fourth. Okay. And then here you have opposed cylinder type of engines. So you have 1, 2, 3, 4 cylinder, but they are arranged opposing each other 2 by 2. And this one is a V shape, so you have the 3. So you have 3 on the left and then 3 cylinder on the right, but they all share the same crankshaft, which means that whatever is happening inside the cylinder will produce the required motion to the crankshaft, and then this is then at the end of this will be connected to the powertrain. Okay, so this is how you classify the engines. The first one, SI or CI, and then you define, is it 4-stroke or 2-stroke, and then you can further define, is it this, what will be the arrangement. Okay. Is it 2 inline, is it V shape, or is it opposed cylinder, is it opposed piston, and so on. Okay, so this is how you classify the internal combustion engine. In actual cycle, so it's difficult for you to analyze due to the presence of complicating effects such as friction and so on. And then it's easy for you to assume that the working fluid remains as gas throughout the entire cycle. And then if in real cycle, you need to really analyze the chemical process that is ongoing. So for example, if you have the mixtures of petrol and air, so you need to know how does the petrol is behaving when the oxygen is at its presence, and then what will be the order of action and so on. So there will be a lot of things to consider. Okay. And then the working fluid does not undergo a complete thermal cycle, because some of it will be thrown out of the engine point as the exhaust gases instead of return to the initial working state. Okay, and the actual cycle we assume is happening as a open cycle analysis. So to make an analytical study of the cycle practicable, so some complexities are kept at a manageable level, and then we need to utilize some idealization. So which means that we need to to create some assumptions. Okay, same as the theories and concept of reciprocating compressor. So there are assumptions that you need to take into account when you want to do the analysis for the internal combustion engines. Okay. So such cycle is called as the ideal cycle. So if you notice for the thermodynamics too, we have the Rankine, Brayton, and then we have the reciprocating compressor, which is the air standard cycle. Okay. And then we have the refrigeration cycle, okay, where you have different type of refrigerants working on. And then for the internal combustion engines, a similar approach. So you have on top of the air standard assumption for the internal combustion engine, you have two more, which is the Otto cycle and the diesel cycle. Okay, and if you notice in thermodynamics too, all these are the ideal cycles, because you want to use the ideal approach to provide the understanding for the actual engineering devices. So you use that the cycle as your target, as the benchmark for the analysis. Once you have the system running and start to produce meaningful work, then you then compare between the actual system and the ideal system, what is the gaps and how you can improve the performance. So when we use the ideal cycle to understand the internal combustion engine process, so these are the assumptions that we use. First, the working fluid is air. Everything is internally reversible, and the combustion process, which in actual cycle is based on the chemical reactions, we simply assume that everything can be reduced as a heat addition process from an external source, and then we replace the exhaust gas by a heat rejection process. And this is what we call as the air standard assumptions. So this assumption is almost similar when we take into account the analysis on the Brayton cycle for the gas turbine. Okay. We don't look in detail on how the fuel is being supplied into the chamber, combustion chamber, but we assume that the process is taking place as a heat addition process, and then once you completed the combustion process, the resulting byproduct is what we call it just a heat rejection process. So by having this assumption, we then can call it as the air standard assumptions. Another assumption is assume that the air has constant specific heat, and then all the values are determined from the room temperature. So if we use this assumption, so this is a cold air standard assumption. So this is the second assumption. This is the first assumption. Those two ideal cycles will assist the understanding on the internal combustion engine process and behavior. And then we have the Carnot cycle as before. Why we need to have the Carnot? Because again, the advantage of the high temperature reservoir and also the low temperature reservoir. But why we cannot use the Carnot cycle? Because it related to the hardware issues. And secondly, to achieve a reversible isothermal heat transfer is very difficult, because you're going to require a very large heat exchanger and it will take a very long time. But why we bother? Because we want to know the temperatures where the system or the device is operating. As long as we know the delta T, the temperature differences, then we can make an estimate how is the efficiency of the internal combustion engines. Right. Before we end for today, just a brief go through on the Otto cycle. Okay. So Otto cycle, why we have the Otto cycle? Because we want to approximate the spark ignition process. Okay, so for spark ignition engines, the ideal cycle is Otto cycle. Okay, so in the PV diagram, this is how you sketch the Otto cycle. So this is initial volume. Volume is reduced. We have the compression stroke, and then the spark initiated the combustion. So the resulting explosion pushed down the piston. So the piston moving downwards to increase the volume, and then once you start to dissipate the exhaust outside the cylinder, you reduce to the initial pressure, and then you repeat the process. So in this Otto cycle, you assume the pressure addition process is happening at the same volume, because it's a constant volume process. Okay. P2 to P3 is happening at the minimum volume, and then the reduction of pressure from P4 to P1 is happening at the maximum volume of the cylinder. So this is the Otto cycle assumptions. Okay, 1 to 2, the isentropic compressions. 2 to 3, constant volume heat additions. Okay. Same volume, you have the heat addition process. As a result, P will also increase. Temperature supply is increased. So as a result, you're going to increase the pressure. Then once you have the combustion happening, and then you have the 3-4 process, which is the expansion. The expansion means that the pistons is going downwards. Piston going downwards, so that's why you have the increase in the volume, because piston is going downwards. And then you have the 4 to 1, which is constant volume heat rejections. So you have the QR here. Here you have the Q in. Right. So in the Otto cycle, the working fluid is alternately expanded and compressed in the piston cylinder device. Okay. Using this PV sketch, then we can then work out the equations related to the closed system for the Otto cycle analysis. So you have the compression stroke 1 to 2, 1 to 2, so temperature increase. Okay, and then the heat addition process due to the spark ignition process, pressure increasing again, but the pressure also increase at the same volume. And then the expansion, you will start to move the piston downward because of the force and pressure from the explosion. Temperature drop because the conversion of energy is happening. And then you close the cycle when you get rid of the exhaust, and then the temperature further downwards, going down, but going back to the first initial. So this is the TS sketch. This is the PV sketch for the Otto cycle. And similar as others, you're talking about enthalpy and also talking about the temperature values. Okay, I think that's all for today. We continue tomorrow. We have another half of the lectures, and then yeah, tomorrow inshallah we continue for the remaining